As we know, sometimes when we're dealing with linear systems, sometimes when we graph the different lines, the lines may not cross ever, so there will be no solution to the system, or sometimes the lines are the same lines, which we refer to as coincident lines. In that case, we've got the solutions are all of the ordered pairs on that graph, so we end up with an infinite number of solutions. So seeing what that looks like when we use the elimination method is really important to recognize. So let's go ahead and solve these particular systems using the elimination method, and we will kind of get some special cases with these examples. So yeah, with this first one right here, if we're to use elimination method, it's nice to get these equations into standard form. So I'm going to rewrite that first equation as negative 3x plus y equals negative 9. The second equation, I'll keep it as is, so 12x minus 4y equals 36. So now if I add the left-hand sides together, we're not going to eliminate anything, I guess. So we'll have to create some opposites. So let's say that we want to eliminate the x's. Negative 3 does go into 12 4 times, so we can create a negative 12 if we multiply by a 4. So we'll do that to both sides. So negative 12x plus 4y equals negative 36, rewriting that first equation. And then 12x minus 4y equals 36 is the same second equation. So now if we add both sides together, negative 12 plus 12 is 0, 4 plus negative 4 is 0, and negative 36 plus 36 is 0. So we've actually eliminated like everything. There's no x's left, there's no y's left. So we don't really know like what x's and y's are, the values of them are going to be, right? So what we do realize though right here is this is a true number statement because it does simplify to be 0 equals 0. So when that happens, that does tell you that these equations are actually the same equations as each other. So like if I were to solve this equation right here for y, you could see that it becomes this when I first get the negative 4y alone. And then if I divide both sides of that by negative 4, you end up getting this equation. So when you look at those two equations right there, you can see they have the same slope and the same y-intercept. So of course they're the same lines as each other. So what we're seeing then is that the solutions to this system are going to be all of the ordered pairs on basically y equals 3x minus 9, because both of the equations were actually 3x minus 9. So when you get a true number statement like that, it'll be all those solutions. In terms of how many solutions, of course, we have an infinite number of solutions, of course, going to be on those graphs. And then for the other one here, let's say that we're going to try to eliminate the x's again. How about so both the negative 4 and negative 10 are the coefficients. 4 and 10 are both going to go into like 20. So how about if we multiply this first equation by 5 then, because then we get negative 20x plus 50y. Multiply that side by 5 as well to keep it balanced. And then if I want opposites, I'm going to multiply this here by a negative 2 because I want it to become a positive 20, and negative times a negative. So then negative 2 times that would become minus 50y, and then multiply that by negative 2 to become negative 32 on that side. So now, if I go ahead and I add both sides together, I get 0, and then plus 0 equals negative 13. So 0 equals negative 13. That's obviously a false number statement. So what that will indicate is when you're using elimination and you come up with something like that, a false number statement, then that's going to indicate that there will be no solution to the system, because actually if you were to solve this equation and this equation for y alone, you'd find they'd have the same slopes. But the y-intercepts of those lines are going to be different from each other. So therefore they're not going to cross each other. So we can just say then at this point that there's going to be no solution to this linear system, which of course tells you there are no answers to this whatsoever, since there's no solution.